So I'm just finding where the nodes. So it's basically show you the material that I will be using for it. So I think it's in the lecture notes all. And maybe let's go towards somewhere around let's say 200. That's backstepping. Yeah, so this paper here, I'll download it. I'll upload it for you. I think they never published it, or I don't know if they published it, but this is the notes. Okay, so because it's a real problem now, you will have lots of bookkeeping. It will involve vectors and matrices. So kind of. Okay, let's get started. So that's a UAV problem, like a simple one-dimensional problem, right? Or two-dimensional problem. So again, the process that I want you to understand is the bookkeeping part. Like how do you kind of arrange your terminology so that things are very easier. Okay, let's get started. So this is UAV 2D path planning using adaptive backstepping. Okay, so let's get started. Okay, so the problem description is here. Let's me write the problem here. So we are given let's consider a fixed wing UAV flying at a constant altitude. Okay, so the height doesn't change, and you can change height in over the spring break. And so the problem is like this. So you have so the position vector or position z dot, the position vector is given by v of s psi. Like it's a shorthand notation, right? So v is the velocity, which is nothing but v cos psi and v sin psi, right? Shorthand notation is necessary because now you see you will be writing those bookkeeping. So instead of writing this, I might want to write this. So v into s. So the s psi is this. So the cos psi, and so s psi is cos psi sin psi. Okay, so similarly, if I say s prime psi, what will be that? S prime psi will be minus sin psi cos psi. So shorthand notation so that our writing and everything remains in a normal way, right? So that's the position vector. It can also be considered Pn dot Pe dot, right? Pn dot Pe dot position northeast, right? So that's the first part. That's the simple position equation, and then you have your, so that's one equation, and then you have psi dot, which is how does the turn rate varies. So turn rate, basically there's an autopilot, right? So the autopilot can be considered modeled as a first order autopilot. There can be a second order autopilot, first order autopilot. So if you, I don't know, you might remember the simpler guidance models where we are using first order, second order autopilot. So that is like it has alpha psi, that's the gain of the autopilot. It's a proportional controller, and it's psi commanded minus psi. So that's the autopilot, right? Simple. So the input is psi commanded. So you give a psi commanded, and it takes some time and converges to that value. And similarly, we have v dot. So is alpha v. You give it a v commanded minus v. So this is what you do, right? What commands do you give in autopilot? You say, hey, fly at this heading. So you always give a commanded heading to the UAV autopilot. You buy an aircraft, and and the autopilot will take these commands. What height you should fly? What if you see chapter 6 assignment? What are the inputs? The heading, course angle, the height which you want to fly, and then what is the velocity at which you want to fly. So that's the simplest UAV. So we have 4 states in our system now: PN, PE, psi, and velocity. Okay, so that's the thing. So S, that is S of psi. You can put a bracket so that you know that it's a function. Okay. So now the idea is, so the objective is to track a trajectory, a desired trajectory given by these equations. So this objective to track a desired trajectory given by z, again zd dot. So I'm saying the desired trajectory is governed by these equations of motion, which is v desired, s psi desired. So similar. This is like this function, but now instead of this, v desired is there, and psi desired is there, right? So it's and then your psi dot desired equals to some input u. So the desired trajectory can be controlled by u. You can, whatever you want, you can make a sinusoidal trajectory, you can make a circular trajectory. If u is 0, then it's a straight line, right? Because that's the turn rate. So you can control that, and v desired dot equals to, so it's a constant. So the trajectory is a constant velocity trajectory. So what are you doing? Like, you will have to solve this to in a S function to give you a desired trajectory, basically, right? If you put it in, it will give you P like ZD and psi desired and everything, right? So you can put it in a S function and get a desired trajectory. So that will be the output of that function, all these. So again, the desired trajectory also have 4 states, but the velocity is constant, and okay. So now the objective is to track the desired trajectory, and this is the objective. So that means we have to solve for phi commanded and v commanded. What should be phi commanded and commanded such that we track this trajectory? That is the objective. So you have to solve for v commanded and psi commanded. Got it? So that's our simple problem we have in our hand. We have to solve what should be commanded. So you have to change the commanded velocity and all that, such that I track this trajectory. Questions? Move forward. Okay, so let's get started. So if you see, to start with, what is we have, so there are 2 different approaches. You can actually formulate the problem in error coordinates, right? Or define the Lyapunov function in terms of error coordinates. So the first is, let's say, step 1 is called tracking part. So if you see, we have this equation, right? Z dot equals to Vs psi, and the idea is to track Z dot desired dot, which is equals to V desired S psi desired, right? So that's the idea. So we can because it's a backstepping problem, right? So the first equation of motion does not have control in it, right? It's a function of V and psi, which, like, if you remember what was it, like x1 dot equals to x2 and x2 dot equals to u kind of thing, right? So this is this equation. So your x2 is like v and psi, not exactly that, but a nonlinear function of that, right? So we can consider, let's so the simplest idea will be, okay, what if we consider, if in your differential correctness, if you remember, we used to consider that the whole nonlinear thing is some input. So first you solve for that input, and then you can do inverse mapping to solve for v and psi. right? You remember that? The quad rotor trajectory where you had this all sine theta cos theta term, but you say, okay, whole of this thing is some u. So it becomes linear then. Equation becomes linear, and then you can go and so something like that. We can say that this is the input also, right? So what should be this such that z goes to z desired? That can be the case. So we can first do that step one tracking. We can say, okay, let's. So objective is to make z minus z desired go to 0. That's the whole objective. What should be velocity and what should be the heading such that this goes to 0. Okay. So for that, our first Lyapunov candidate function v1 will be half of z minus z desired squared, right? Or this is like error squared, right? There's nothing big. Error squared. Position error squared term. So what will be v1 dot, or this can also be written as half z minus z desired transpose into z minus z desired. Same thing. Okay, so if we want to find v1 dot, then next step is v1 dot, right? So v1 dot will be just like z minus z desired and in z dot minus z desired dot transpose. Half goes away because you have to do it two times, right? For example, if you keep it half here and then you do another half where you say z dot minus z desired dot into z minus z desired, they are both same, right? This and this, because they are scalars. So basically you can get rid of one and remove half. Same thing, right? So okay, basically error dot, right? This is what? This is, if this is error dot, right? So you can do either way, but so now we can plug things in. So z minus z desired transpose into z dot is v of c psi, or s psi minus v desired s psi desired, right? That's the equation. Okay. So now question is, if we say, let pass. So what we are saying, like, let's say this whole thing, this what is this? This is a 2 into 1 vector, right? All of these are 2 into 1 vector. So this whole thing is 2 into 1 vector. Even the whole multiplication. And multiplication is a scalar now, of course, but this is a 2 by 1, like 1 by 2 vector, and this is 2 by 1 vector. So we can say this is a u or something, right? Or zeta or something. Some whatever coefficient you want to name, you can name it. So this, let's say this is zeta, and you want to find zeta desired such that this becomes negative definite. So till here things are simple. Like, so we can say, okay, our zeta, this whole thing will be, so your zeta can be, I'm choosing this. What should I choose? So first thing will be cancel this out, right? So that will be v desired s psi desired, right? And then maybe put some multiplied by some k1 into z minus z desired transpose, right? If I choose this, then what will happen? v1 dot, this will cancel out, and v1 dot will be, if this is the case, then v1 dot will be basically minus of z minus z desired into k1. K1 is a 2 by 1 matrix. So it can be k11, k22. It's a diagonal matrix, but positive thing. So it's a positive definite. So z minus z desired transpose, right? So this is negative definite, because if k is positive definite, k1 is positive, this is negative definite. This whole thing, v1 dot. So that's good, right? So instead of one gain, it's a gain matrix. So you can choose k11, k22, or both same or whatever you want. So that's good. So that means this is what I want this to be, but it is not this. So we have to, you have to go back and add and subtract to the original equation and put it into that z variable, right? So so we can go back now and so what you can do is, what was your equation? Your z dot was what was that? Vs psi, right? That was your z dot. So we can plus minus this, right? This quantity. Where is my zeta? This quantity. So plus zeta minus zeta, right? So like adding a 0 to the system. So if you, so this and this, you want this to go to this, right? So basically the difference between this has to go to 0, right? So that's the idea. So let me see, what are they calling it? Yeah. So this, we can call it Q1. So our Q1 is equals to V of S psi minus zeta. Okay, we can plug things later on, but this is the case. So it can be become, so your z dot becomes Q1 plus zeta, right? And what if you plug in the value of zeta? What is zeta? Kind of the terminology that I have to use. So let's not define Q1 for now here. This is one approach we can do. Let's, because I want to maintain what it's done in the book, right? So Q1 is this, so minus actually this is Q1, it should not be. So yeah, let's Vs psi minus zeta, z dot is Q1 plus zeta. So in that case, you know, and let's plug in the value of zeta. What is zeta? From here it is plus Vds psi d minus K1 Z1 is ZD transpose.
I don't think there will be transpose.
Yeah, no transpose, sorry. I don't know why. No transpose, good. So that's our Z dot. So if we plug that back into our V dot equation, right? V1 dot was, what was that? Z minus Z desired transpose into Z minus Z dot, right? Oh, sorry. So Z dot minus Z desired dot, right? So you can plug now this value, so it becomes z minus z desired transpose into z dot is this q1 plus vds psi d minus k1 z minus zd, and zd dot is again this, so it is minus of vds psi d. Okay, so now what happens, we can cancel this out, right, this and this, and the v1 dot basically is z minus z desired. I think error coordinates would have been better. I'm just using whatever there in the node so that you have something to look for, but error coordinates would have made things a little easier. And this is k1 z minus zd transpose k1 z minus zd, right? So that's the case. So this is negative definite, but we have this term that still sticks there. Okay, Q, where is my q1? Here. Because now we will, in the next step, we will need q1 dot, right? Because now what will be our new candidate function? That will be v2 equals to v1 plus half q1 transpose into q1, right? Because I want q1 to go to 0, right? So what is my q1? Q1 is vs psi minus z, and minus z is zeta is, where is my zeta? Zeta is minus of this, so minus vds psi d plus k1 z minus z desired dot. Okay, so that is our q1. So what will be q1 dot, because v2 dot will be, so we will need q1 dot from here. Q1 dot will be q1 dot will be, let's start taking differentiation. So anything cancelling? No, right? Nothing is cancelling. So q1 dot will be v dot, right? Si, and then plus v s prime psi, right? Differentiation of this, and then here it will be vd dot is 0, so that's okay, and then it will be minus of vd s prime psi desired, and then here it will be plus k1 z1 dot minus zd. Let's keep it there, maybe let's not plug things in to make things complicated, but that's the case, right? So that is q1 dot. So now if we do this, v2 dot will be v1 dot plus q1 transpose q dot, so that whole thing will come inside. Now we can plug in what is v dot and s prime psi, we can plug in later, but what was v dot? I think it was alpha v commanded minus v, right? V dot. So let's first plug it in here so that we have things here. V dot s psi plus v of s prime psi minus vd s prime psi desired plus k1 z1 dot minus z dot d into this. And remember, what is my v1 dot from here? It is minus of z minus z desired transpose k1 z minus z desired, and this, right? So this can also be written as q1 transpose this, because same thing. You take a transpose of a scalar, you get scalar. So I can rewrite, because why I'm writing this, so that I can bring that in. So it becomes q1 transpose z minus zd. Okay. So basically we can bring it in now. So we can bring everything in from here to here. Do you want to go like long, or do you want to go this and this? This okay. Let's do this, right? So it will be where is my z minus z desired, and then whole shebang, v dot si v s prime psi minus vd s prime psi desired plus k1 z1 dot minus z dot d. Okay, so these are the bracket here and here are common. So okay, so now that okay, so what's the next thing? We can plug in these values, right? V dot, and so yeah, we should plug that in. I think we missed something. When you are doing this, right, this differentiation, I'm taking a time derivative of it, right? It should be multiplied by psi dot also, right? And when I'm doing this, it should be multiplied by psi dot as well, whatever that psi desired dot. So that should be that u, is it? Yes, right? So that u thing which we were changed. So what is psi dot desired is u. So u will come here, psi dot will come here, and so let's plug that in here. So it's psi dot, and u will come here, right? Because you also take the time derivative of psi. Questions? Anything? Any confusion? I know, like, so anything I'm doing wrong or something? Anything missing? No, right? Good. So now let's plug in the values. Our v dot is alpha v commanded minus v, and your psi dot is alpha psi commanded minus psi. So that basically comes in now, right? Because now it's a time to choose the control input, so we'll plug this in. Okay, so let's go. So v2 dot then basically is minus z. Yeah, I hate it. It should be errors, so that it at least becomes smaller. Otherwise you'll just keep writing all this. Z minus z dot plus q1 transpose z minus z desired plus alpha v commanded minus v s psi, and then we have alpha psi commanded minus, I'm plugging in this value, right? V s prime psi minus u vd s prime psi desired plus k1 z1 dot minus z dot d. got it finally to this stage. Okay, now we need some because the problem is alpha. So see, my objective is to choose these things, right? V command and psi such that this becomes negative definite, right? Negative definite means you have this Q1 transpose into some Q1 minus of Q1, basically. So this whole thing, this if I use my awesome green color here, right? This whole thing, if it is equal to minus K2 Q1, then your life is set, right? Because K2 is again a diagonal matrix, some gains, positive definite. So this will give me minus Q1 transpose into K1 into Q1. So this is always negative. So I want this whole term to be this. And what is in my hand to choose? I can choose this, this and this. But now it's kind of entangled. Entangled in the sense that I want to choose it in a vector form so that I get the answer in one shot, like both for V commanded and psi commanded, rather than. So now it's very hard, right? If I can choose this to make everything go to 0, and if this is 0, like for example alpha psi is 0, then I can choose alpha V, and then if I can choose alpha psi to make whole thing 0, right? Rather than that, I want a one shot answer. So here is one trick we can apply. So let's write down these just two terms, this and this term here. Like it's separately, because I want to write it as a matrix and vector form. So alpha V, let's use some other color. Alpha V commanded minus V and is S psi, right? So what is S psi? Let's spell it now for at least. S psi is cos psi sin psi, right? And the next term is this, which is plus alpha psi into psi commanded minus psi. And let's did I leave anything? No. So into V, so V can come outside, so V into minus sin psi cos psi, right? So I have to somehow combine this term together so that it becomes a vector form. So the one thing that looks, what I think can be done here is this. So this and this can be made combined together and made as a vector. So what it looks like? It's a column multiplied by a scalar. It's a column multiplied by a scalar, right? This can be represented if it can be like something like this. Let's say you have a matrix, right? A11, A12, A21, A22, right? There is a matrix, right? And this is one column, this is second column. So this column is multiplied by x1, and this column is multiplied by x2. That's what. So this is x1, whole thing is x1, or this is x1, this is x2. So this can also be written as like this, right? A matrix multiplied by x1, x2. So that way your controls will come here and it will be multiplied by a matrix. So now this whole thing can be written if you combine, if this and this can be combined together. So I can write this as cos psi sin psi minus v, velocity comes in here because of this, so minus velocity sin psi velocity cos psi. So this is a matrix multiplied by alpha v alpha v commanded minus, in fact you can also, because alpha v and all also can be, one more thing can be done here is this. So this is kind of a, like when you are deriving these things, the research is not about, you have to solve these things, like you have to come up with these tricks to make things simpler so that you get some kind of So now, see, it's multiplied by this, right? Alpha v, where is that? Alpha v, v commanded minus v, and alpha psi commanded minus psi, right? But again, I can do one more trick. This can also be, so this is called R psi. I can say this is a rotation matrix kind of, not exactly rotation matrix, but I say this is R psi. So that will make my notation small, and this here can also be written as a multiplication of a diagonal matrix. See, remember, we don't know alpha v and alpha psi. That's one important thing I should have told earlier, but we don't know alpha v and alpha psi. So this is our theta. So I have to separate it out. I have to separate this theta out so that when I do the cancellation and all, this is there. So I should write this as alpha v0, 0 alpha psi multiplied by v commanded minus v psi commanded minus psi. What? This is awesome, right? So this is equal to this, right? When you multiply this alpha v into this, and when you multiply this alpha psi into this. So this, the whole thing can be written as a diagonal matrix multiplied by a vector, right? Right, guys? So this can also be, we'll see, this is our theta matrix now, if you see. So it will come as R psi into theta, because that theta is unknown, and we can estimate that thing also in one shot rather than doing it separately. So now we can do this simplification and plug things back here, which will become simpler now. So instead of that, what we will write? We will write R psi, this whole thing is equal to R psi, which is defined here. This is R psi here, and some, I don't know if they call alpha v something. Let me check. Yeah. So some, you can call it like gamma or something, where so this thing. For now, let's just keep it as alpha v 0 alpha psi multiplied by v commanded minus v psi commanded minus psi. So this whole thing, these two things can be written as this one multiplication. Okay, now we can plug things in, right, in here. So that will be, so my v2 dot will be now minus z desired transpose k1 z minus z desired plus q1 transpose z minus z desired plus this whole two terms, this and this can be written as R psi into this alpha v 0. You could have written it like gamma or something like this. This whole thing can be like gamma or something like that. And v commanded minus v psi commanded minus psi. So it kind of separates out the unknown parameter multiplied by control input. And then what is remaining? Then remaining parts are u v desired s prime psi desired plus k1 z1 dot minus z, oh not z1 dot, z dot and zd dot. Okay, so that's our term now. So again, the objective here is, what is the objective? To make it like something equal to minus k1 k2 q1, right? Something like that. This whole thing should be, so the only thing that I can choose now, so I have to choose this, but the problem is this is multiplied by unknown matrix, if you remember, right? So that's the issue here. Question so far? So see, we have kind of simplified things so far, not a big problem. Now, let's come to this point here. Let's assume you know this for now. What will be your control? If I tell you that I know alpha v and alpha psi, what will be your control? Or what will be the choice of v commanded minus v such that I get this? What will you do? See, you can say this term, you can cancel this out, you can cancel this out. Right, so I will say r psi alpha v 0 0 alpha psi v commanded minus v psi commanded minus psi equals to cancellation of this, so that means u vd s prime psi desired, right, minus of this minus k1 z dot minus zd dot, right, and minus of this minus of minus of z minus zd, so that cancels out everything, right? And this, I'm choosing this whole thing such that and then equal to minus k and also minus k to q1, so that gives me, so if this is the case, so I can choose this, right, and that will give me a negative definite thing, right? That will give me my v2 dot to be, this is z minus of z transpose k1 z and minus q1 transpose q2 q1. That's negative definite, right? So I will get that. Now the question is, yeah, that term is okay, but now this is my control, so I have to choose my control. What will be that? That will be v commanded minus v. I'm assuming that I know this for now. And then psi commanded minus psi equals to, you can take, so when you do this, it will be r inverse of this. So this, if you just multiply this whole thing will be multiplied by r inverse, and then first r inverse psi, and then inverse of this is 1 over alpha v 0 0 1 over alpha psi multiplied by this whole thing, right? U v desired s prime psi desired minus k1 z dot minus zd dot minus z minus zd minus k q1. So for to make your life a little easier, let's call this term as q2, so that things are easy. So this is q2. So then I can rewrite this, and it is 1 over alpha v 0 0 1 over alpha psi r inverse psi into q2 minus k1 q1. Life becomes a little easier in that sense, so that I don't write again and again, right? So that's my v commanded. If that was the case, then your game is over now. You would have solved the problem by now. So this is if this is known, this is my control input using backstepping, nothing else. Backstepping, it's called feedback linearization, whatever you want to call it. So this is your answer. That's the controller that will achieve target tracking if you exactly know these parameters. The question is, this is not known. So if this is not known, you'll have to do an estimate, alpha v hat and alpha psi hat. Use that, and then we'll take it from here in the next class. Right? I think Saikat is also waiting. So, is it time? What time is this? 2:28. So we'll go over this, at least get it here till this point. And in all notes, lecture notes, all I think is page number 204. you can remember, I don't know, but you will find out this is like a paper. So we'll go from here. Now things are just now the adaptive control part is there, because if this is the case, then when you plug this in, then that error between actual theta minus theta hat, then you have to make that go to 0 by adaptation law, and then you know. Okay, so this is this, and we will next class we will also simulate it and see how nice it does. And you can finish this homework in next week before the spring break. So yeah, next week let's take it easy. Take it easy in the sense, yeah, not.
No, I need it because the other class is pretty demanding next week.
So we'll just do one class next week. That's the Monday, because we have to finish it.
Okay.
Finish it, and then let's say Wednesday and Friday classes, you can just come and ask questions on the homeworks rather than having actual two classes, so that you prepare for your spring break.
That's
exam.
appreciated. Sure.
Okay. It's hardcore, so I'm thinking. The good part about this class is you don't have to prepare. You prepare as you go. Right? It's all derivations. Okay, good luck. I'll post this recording here. So this is where we were, right? So what I wanted to say was that if alpha v, alpha psi were known, then there was no issue. This was the final controller. This could have solved our problem, like given us this is still a final controller now, but you will have to estimate these things, right? But if they were known, then we could have gone. Our V2 was negative definite, right? So this is where we were. Let's see. Okay. Okay, so let me just rewrite this thing. So now we are at the phase, now we have to adapt, we have to do adaptation, right? Adaptation is what we need to do. So what we can do from here is, so now we can call this as, so 1 over, we're just defining, we can call theta equals to 1 over alpha v 0 0 1 over alpha. So basically theta equals to 1 over alpha v. Instead of estimating this, we are estimating 1 over alpha psi, right? And theta hat will be 1 over alpha v hat and 1 over alpha psi. Okay. So how can we write this now? This matrix. This matrix can be written as diag. You know diagonal command in so what is diag theta means? Means this, right? Means I'm putting a vector as a diagonal of a matrix. So that means diag theta. So we can write this matrix as diag of theta, and this matrix as diag of theta hat, right? No issues, right, with that. So just having said that, what we can do is now we can so coming back to V2 dot, right? Where is my V2 dot? Yes, here. So we can add and subtract let's see. did I say what was Q2? Before we were somewhere. Here. Yeah, this here. U V D S prime. Just want to see what my Q2. Q2 is V. Okay, UV desired. Yes. Z minus Z desired. Yes. Minus Z minus. Okay, let's step back a little bit here. Here. So this term. So can we rewrite this thing? Let me erase all this stuff for. Just want to match my notes. Oops. Oops. Anyways, let's go back here. What I'm saying is, before we even move there, it's V2 dot equals to minus Z desired transpose K1 Z desired plus Q1 transpose Z desired plus R. So I'm writing, so I'll put this at the end, or we can put at the beginning, but Z minus Z desired and all the rest of this term, right? Minus U V desired S prime psi desired plus K1 Z dot minus Z desired dot. Okay, plus this term plus R psi alpha V0 alpha psi and VC minus V alpha psi commanded minus psi. So this is it, right? So what we are saying is this is Q2. Just okay, so we can rewrite this. V2 dot equals to minus Z desired transpose K1 Z desired plus Q1 transpose Q2 plus R psi alpha V00 alpha psi V commanded minus V psi commanded minus psi. Okay, so now if we have to choose, so we can say this, we can choose this R psi into alpha V00 alpha psi Vc minus V psi commanded minus psi equals to minus Q2, right? So that cancels out, and minus some K2 into Q1. Okay, so this will give me V2 dot equals to this will give me V2 dot equals to minus Z desired transpose K1 Z minus Z desired minus Q1 transpose K2 Q1. So negative definite, right? But unfortunately, so that means we can compute for this, right? So Vc minus V psi C minus psi equals to equals to, what is that? Equals to R inverse of psi of this term, right? Minus. So I'm just trying to compute this quantity. So first R inverse, so that multiplies this, and then inverse of this Q2 minus K2 Q1, and multiplied by 1 inverse of this quantity, 1 over alpha V 0 0 1 over alpha psi. Okay, so that's our controller. If things are known, then we'll get this, but unfortunately that is not the case. So our controller can be written as I can write it in red, Vc minus V psi C minus psi equals to 1 over alpha V hat 0 0 1 over alpha psi hat. Okay, so this is the actual controller, R inverse psi minus, because these are not, this is not known, unknown, minus Q2 minus K2 Q1. Okay, so that's the case. So now let's plug that back in, because it's not the case. So we can do is we can add and subtract that term. Yes. So what we can do is just rewriting this part here, V2 dot. Okay, so that how we will write is V2 dot equals to minus Z desired transpose K1 Z minus Z desired plus Q1 transpose Q2 plus R psi so we can plug this in, right? So because that's what if you see here, this value we can just substitute by this quantity, right? So then it becomes R psi alpha V 0 0 alpha psi, and when we plug this in, it becomes 1 over alpha V hat 0 0 1 over alpha psi hat, right, into R inverse psi. See this, if they were known, right, then this will be identity matrix, right?
Right.
But that's not the case. And then this and this will be identity matrix, but that's not the case. So Unfortunately, we'll have to deal with it. Minus K2 Q1. So that's the part we have, but now you can add and subtract just so that we can, the idea is to get that difference, so we can add and subtract the original thing, so that is 1 over R psi alpha V 0 0 alpha psi 1 over alpha psi alpha V 0 0 1 over alpha psi R inverse psi minus Q2 minus K2 Q1. So that's minus, right? I'm just adding a 0. R psi alpha V 0 0 alpha psi 1 over alpha V 1 over alpha psi R inverse psi minus Q2 minus K2 Q1. So the idea is to get a difference between the real one, the estimated minus this. Like we can get the difference between those two quantities, and then so now, so we'll this and this we can use, but what will be this quantity? This is whole quantity is identity, right? So this and this is identity, this and this is identity. So total, the whole thing is identity. So now we can write V2 dot. So this can be taken out basically. This cancels this out, right? So this is identity matrix, right? Just in blue. This whole thing is identity matrix. So basically this remains. So this remains means this cancels out, and this, so it goes out. So it becomes basically this, we can cancel this out, we can cancel this out, and this multiplied by Q1 goes out. So V2 dot is Z minus Z desired transpose K1 Z minus Z desired minus Q1 transpose K2 Q1, and then we can go back again in the bracket. So now this term is left and this term is left, right? So we have to deal with it. So that is Q1 transpose R psi alpha V 0 0 alpha psi 1 over alpha V hat 0 0 1 over alpha psi hat R inverse psi minus Q2 minus K2 Q1. Okay, so now see, in this we can take these couple of things common. If I write again this is minus R psi alpha V 0 0 alpha psi 1 over alpha V hat 0 0 1 over alpha psi. No hats are there, just alpha V alpha psi R inverse psi minus Q2 K2 Q1. So see, now I want to take things common, right? So common things will be, so common things will be in both the cases this, right? And this and these two, right? So 2 in the back that side and 2 this side, right? Since it's a diagonal matrix, it doesn't matter if I multiply this side or this side, doesn't matter, right? So what we will do is if we take things common, it will be just let's not write this part, just I'm focusing on this part. So it is 1 plus, so dot 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 plus Q1 transpose, I'm taking R psi common, and this common, alpha v zeros. Good thing about common thing, anything if we can multiply this with 0, this will go out. So it doesn't matter if we know them or not. So this, and then R inverse psi and minus Q2 minus K2 Q1, and basically this minus this, right? So this minus this will be
And as the hat approaches that
Mhm.
value, your estimates get closer to the actual value, it all goes to 0 and everything falls
Mhm.
out.
Mhm. So actually this, what I forgot was, yeah, so basically you can write 1 over alpha v hat minus 1 over alpha v 0 0 1 over alpha psi hat minus 1 over alpha psi, right, multiplied by this, okay, or multiplied by the outer one. So this here red thing is this bracket, one more bracket. Okay, this can also be written as so what happens when I multiply this matrix with these two? These are, so this is 2 into 1, right? This is 2 into 2, and so I get the same thing basically. So this whole thing can be written as diag, because of this 0 0, right? This will be multiplied. See, the whole thing will come. The whole matrix multiplication is a diagonal matrix. So if I multiply this into this into this is a diagonal matrix, because of, if you can see, because of these 0 0. When I multiply this, I again get a matrix which is 0 0 this. When I multiply this again, I get a matrix which is 0 0. So I can write this whole thing as diag of R inverse psi minus Q2 K2 Q1, right, into theta hat minus theta, basically. Theta hat is 1 over alpha v hat, 1 over alpha psi hat, and theta is 1 over alpha v and 1 over alpha psi. Okay, so see, so diag of this whole thing can be written as that. So now I can rewrite this thing again, Q1 transpose R in R psi into alpha v 0 0 alpha psi diag of R inverse psi minus Q2 K2 Q1 theta hat minus theta, and this. Okay, this is our thing. Okay, so now next, what do we want to do? If we want this theta to go to 0, right? If it is 0, then everything disappears, right? This whole thing disappears, and then we have the nice, because now if you see, this part is there here, right? Z minus Z transpose Z minus ZD minus Q1 transpose K2 Q1, right? So if we are able to make this 0, with this goes to 0, if this goes to 0, right? So now we can make our Lyapunov candidate, new Lyapunov candidate function, so which is V3 equals to V2 plus alpha gamma. What is it? What is alpha? Let's see. Some tuning parameter for now. Alpha, gamma, theta hat minus theta transpose and matrix alpha v00 alpha psi, because I know this will cancel things out even if I keep it here, theta hat minus theta. So this is positive definite, right? Because this is positive definite, right? These are two constants, but this is positive definite. So that's my v3 and this is my v2 dot. So now we can do is v2 dot equals v3 dot equals to v2 dot, which is this, plus we can have plus this is gamma this is an error here in the type paper. I think this we don't need this. So for now let's just take gamma. So this will be this theta hat dot, right, minus theta dot and alpha v 00 alpha psi theta hat minus theta. Remember theta dot will be 0, right? What is theta dot? Theta is constant, so theta dot has to be 0. So this will be equal to, so this is 0, right?
So you differentiated the first term one?
So v2 dot, yeah, this is not there, so first term, so you can multiply it by 2 or something, right? Doesn't matter. So this can be 2. It's a squared term.
Yeah.
So once you do this and then once you do this, both are same scalar number, so you add it, you get twice here, or anything outside will not matter. So I think okay. So let's not have 2 here. Let's just have a gamma, because 2 into gamma can also be considered as gamma. Like that's one parameter. So gamma is there. So alpha, theta. So this is 0. When this is 0, we can rewrite, right? We can plug in the values of z v2 dot, z minus z transpose, k1 z minus z desired, plus q1 transpose, all this r psi alpha v00 alpha psi, plus now into diag of r inverse psi q minus q2 minus k2 q1 theta hat minus theta. Okay, so that's our minus q1 transpose k to q1, and so this and this are together, so this is here plus okay, and plus this, and now we can write this, right? So it is plus gamma, this will go 0, so this is theta hat dot alpha v00 alpha psi theta hat minus theta. Okay, so now if you see, this can be common, right? This can be taken common, so so that means we can choose. So now I have to choose this, right? What should be this such that this whole thing disappears? So that will be equals to, so basically minus of this, right? Minus of this so this, so minus of this quantity, minus of this quantity if I say alpha theta hat equals to, am I missing something here? So this multiplied by this can be taken like they are kind of same.
So that theta hat minus theta is inside the diagonal.
Yeah, that's inside. Which one is inside the diagonal?
The upper one.
So yeah, it doesn't matter. Like this also is kind of a diagonal. So if anything is inside diagonal, right, I can write this as. So if you see, let's just write it. So it is alpha v0 0 alpha psi theta hat minus. So we also have to write this as a diagonal. Like we can write this like diag. This whole multiplication be written as a diag. Theta hat minus theta also doesn't matter, right? So this can be written as a diagonal of some thing, and equals to this q1 transpose r psi. This was outside and this is inside, so we can take this, right, this and this common outside. So it is diag r inverse psi and minus of q2 minus of k2 q1, right, and then plus gamma theta dot multiplied by this whole thing, alpha v so this is multiplied here, q1 transpose, this is multiplied by this quantity. And alpha v 0 0 alpha psi diag of theta hat minus theta. So this is outside, this is outside. Now we can choose this.
The first diag, what's inside of that? Just the R, also the q2 minus k2 q1.
With this one?
Yeah, what's all inside the diag?
Yes, so diag is this R, this whole thing.
Okay.
Blue, let me say blue. This. So now I can choose, right? So this negative means this is totally negative, right? So we can make it plus. So we can choose theta hat dot equals to minus of r psi diag of r inverse psi. So remember, see this negative, we can take it outside and it becomes plus. So it will be r inverse psi of q2 plus k2 q1, right? Diag. That's it. If we choose this theta hat dot to be this 1 over gamma. So 1 over gamma into this quantity. I should not confuse this. This is 1 over gamma. So this will make everything go to 0, and then only term remaining will be this negative definite term. So this is our adaptation law, right? Theta hat dot equals to r psi diag of this quantity. So everything in this quantity is known, like r psi is known, nothing is there which we don't know. Q2 and Q1 are there. So that's the case, right? So remember what will we get? So if you see our u was this. Jesus. Where is my this? This is my controller, right? So and 1 over alpha v and alpha psi hat will be estimated by theta hat dot we just derived, right? So we can rewrite this whole controller, I think, going back, and that is, so see, we are saying our theta hat dot equals to 1 over gamma diag of r inverse psi q2 plus k1 q1 kind of into R transpose psi into Q1 so diag is only of this term, and then R transpose Q1, and then your V commanded minus V and psi commanded minus psi is equals to this 1 over alpha V hat 0 0 1 over alpha psi hat. So alpha V hat and alpha psi hat are like coming from here, right? Like the S function, there are 2 into 1 equation. So first is 1 over alpha V hat, second is 1 over alpha psi hat. This into R inverse psi of minus Q2 minus K2 Q1. Okay. So remember now V commanded minus psi, we have to compute for this. So this will be V commanded minus psi commanded equals to V plus psi. So original value, whatever that value is, plus this. So that's your controller, which will I think I might have done one error in putting this R transpose psi earlier, but because so everything is known here, right? Anything, so everything except like this, everything in this side is known, this is known. So you're getting an estimate of these two quantities, which is giving you a controller. Okay, so this is, so again the main thing will be the bookkeeping part, like you properly step by step make sure you do the cancellation. So let's see if we can questions, any questions here? Anything?
I have to do it again.
Yeah, you will have
yeah.
to. That's the assignment, right? So this assignment is doing it again yourself and implementing it. And so that is not a problem.